it's really a pleasure. As Professor Rolenti introduced me, I am from Albania, I am from Tirana. In fact, I hope you have visited or will visit Tirana also. I am educated at the University of Tirana, but when I was planning to do my first postdoc officially accepted, in fact, was in Croatia, and it was at Ruđer Bošković Institute. I was planning to go there. I had a nice communication at that time with the director of the institute, Professor Markoçi, and I was very excited to go there because this institute was famous, and still I think it is, because it's well known for environmental monitoring and overall for my field of expertise, which is which was the time electrochemistry. So with that, I would like to say that the experience we have in our area in Balkans, overall, of course, in Albania we have had a great university, and still we have, but countries like yours, Croatia and more, are well known for the great experience in the field of chemistry and more. So I am sure that we all are doing the best, and probably this conference also will have for further collaboration and promoting the research and development you are doing in this area. I'm going to show you a brief introduction first about my center, and also you see here different logos. I'll start first with NanoAlb. As introduced, I am a coordinator of this network of nanotechnologies for Albania, but also for the region, with the idea to become the reference center of nanotechnology in the region, together with my two colleagues and friends, Professor Peter Giu and Professor Majlinda Vasiari, a center that is created by Academy of Science of Albania, and we have here also the president of Academy of Science of Albania, who has been the key person to push the creation of this center that now is trying to do the best. So this is a center, as I said, a virtual center. For the moment, there are 25 research groups from Albania, Kosovo, also North Macedonia, but also we have joint research groups, one from Italy and one from Israel. And we'll be very happy to have also groups from other countries in the region. So if you have any willing idea on this topic, so would like to collaborate, we are very much interested to create excellent groups working in the field of nanotechnology. So this center, as I said, in addition of being an excellent center in the region, the idea is to help in overall in creating the new model of research and development in the region, but also to attract talents all over the world, not only local people from the area, but also other foreigners, because the center of such kind of center should be international, and we should try to avoid nationalities in the center, so just international, and this would be fantastic. Of course, giving priority to people that want to turn back home in the area, but with a center with the status of international center, that would be really very helpful. And of course, working in different areas of nanotechnology, being also environmental area, very, very important for this center. So if you have any question about this, or would like to have more information, or would like to propose this to other colleagues, so please write me and we'll discuss this further. But also you have information in this website of NanoAlb, so you can see the different research groups, so what they do, the activities. We are doing a lot of webinars also. We have last time invited Professor here to give a seminar, so you are all invited to collaborate. Now, moving to my center, I'd like to very briefly explain what my center, because I'm based in Barcelona. This is the Catalan Center of Nanoscience and Nanotechnology, the biggest one in nanoscience and nanotechnology in Spain, but also one of the most important in Europe. So we are in a campus of university. This is the Autonomous University of Barcelona campus, where you can see here different centers. So here is our center, this green one. We have a center of materials, microelectronics, it's all here. And also we have a synchrochromic center, which is very, very important. So around 750 scientists working in the area of nanoscience and nanotechnology. So this is a big center, as I said. So with the idea to do research in the frontier of knowledge at the nanoscale, but also we have a lot of concern about technology transference, and of course innovation, training, and training is very, very important. So PhD programs, nanoscience and nanotechnology programs that we are trying also to adapt the same excellence model in NanoArt, trying also to launch a new program for nanoscience and nanotechnology. So in our center, we do fundamental research, but also a lot of collaboration with industry, trying to transfer the knowledge, through spin-off companies, technology transference, and different models of collaboration with industry. So the research in our center goes from the very basic aspects of nanotechnology, so manipulation of materials at the nanoscale, to fundamental understanding of phenomena, and also device fabrication based on nanostructures for different kinds of applications. They go from health, electronics, energy, IT, and different areas. So there are different research groups in our center. So this is what we are trying also to transfer at NanoArt. We have several groups working at nanoscale manipulation and characterization and device fabrication, theory simulation, chemical groups of nanostructures, and also nano biointerfaces and devices in which I work. So these are just the main areas of research of the center. In addition, and this is also very important, as a model, we are part of Barcelona Institute of Science and Technology. You can see here, this is very important about the collaboration. So we are here, and together with 6 other excellent centers, we have created since 4 years this institute. And why? Because in science, if you want to be successful, if you want to have funding, if you want to have a very good science, you need to collaborate. And having this collaboration under a bigger center, we have more visibility, we have more capability to attract funding. And this is why you have seen at the beginning at my presentation a lot of logos, because I am part of different entities, which is quite important and interesting. So going now to my group, I am responsible for nanobioelectronics and biosensors. So we are very much interested in the use of nanotechnology, nanomaterials to develop new devices with interest for diagnostics. And when I say diagnostics, it's not only environmental monitoring, but also clinical diagnostics, safety and security, and other industrial applications. Trying to get advantages of different nanomaterials from quantum dots, nanopores, graphene, carbon nanotubes, and more, and trying to see how these can be used in building different kinds of devices. I'll show you some examples with interest for different applications. And also, as I said, we have interest in technology transfer, and based on our technologies, we have created also 2 spin-off companies, Paper and Graphenic Agave. So our research is mostly focused, as I said, in nanomaterials, trying to understand what happened at nanoscale, what are the properties of nanomaterials, and how we can take advantages of these properties to build different kinds of devices. And we work a lot with, as I said, with nanomaterials, trying to put this onto simple platforms. We work with paper, plastic, so the biosustainability is very, very important. But also we do full integration electronics so as to set up devices and to make this useful for different applications. So and this area is very, very broad. There are a lot of challenges. I'm not going to mention these. One of the most important is in diagnostics, in offering devices for the people to use, is also the cost. So we should be able to offer cost-efficient devices. Otherwise, we are not able to afford, for example, just keep in mind COVID situation. So there was a lot of need for devices, very cheap devices, efficient devices, and we want to deliver these to every part of the world. And this is why cost efficiency is a must for the development of this kind of devices. And of course, as I said, the COVID situation almost changed the scenario when we plan to develop devices for diagnostics. And this is a summary. You can have more information in a recent review wrote at the prestigious ACS Nano, where we talked about what happened with devices. So why we are doing research since many, many years. And then when COVID started and people and the society was needing devices, we are not able to offer efficient devices. And this is because there are a lot of issues. So here, to match the science and business is a long way. So this is through the so-called technology readiness level. And trying to find the matching between these is very important, because you can do a very important, very interesting, from science point of view, device. But if you have not a clear plan for the technology readiness level, and you do not match this with the needs of the market, and also if you do not have support from industry, your technology, your science is going to not to be used, and nobody is going to bring this to the companies. So, and this is why, keeping this in mind, we are working a lot also in the so-called ubiquitous fabrication of nanobiosensors. So imagine, if you have a problem, emergency, like for example, the last one we have for COVID, you need to distribute devices all over the world. What about producing devices in every part of the world? It means that we need to have a simple fabrication capability instead of a very complicated one, like printers that can very fast produce the sensors. So we call this ubiquitous fabrication, decentralized fabrication that allows for these devices to go very fast to the end users. So, of course, one can make the question, so why we need these devices? We have fantastic laboratories. In fact, we have, of course, everywhere there are laboratories, conventional laboratories that are working fine, that still would be always important, because these laboratories are fantastic in terms of sensitivity, information capability, also very suitable for basic research. But if you go for the cost and also time and the necessity for trained user and so on, you fail, because you cannot afford the needs only with these laboratories, because you need to send samples all the time there. And this is why these devices, so known also as point of care diagnostics, are well known, and there is a big demand for them. And in this context, biosensors are a very good alternative to be used as a point of care device. So very briefly, what biosensors are. So this is an example of glucose biosensor. You have seen in any pharmacy in the world, you may see this kind of device, but depending on this, in fact, this is a biosensor. What you put here, either enzymes, DNA, antibodies, or depending on the signal you are going to use. So this is the transducer part. We may either measure electricity, current flowing around, light, you can measure change of the mass, and so on. You may have different kinds of biosensors. So once down the line, you want to detect this interacting, for example, COVID virus with an antibody, or it may be an enzyme, whatever, then the signal is produced here, and you read this in a tiny screen there. So these are very simple. So for these devices to be useful, to be used in places overall with low resources, extreme conditions, you need to fulfill the requisite we call this reassured. So it means real-time detection, easy of specimen collection, affordable, sensitive, specific, user-friendly, rapid and robust, equipment-free, and deliverable to end users. So all these requisites are very important if you want these devices to be successful. So biosensors nowadays can be everywhere. So there is a lot of need for biosensors, and we see these devices nowadays not only as medical devices, but also as wearables, but also everywhere. You see smart TV, smartphone, even smart washing machines, in water monitoring. This is in fact from a project that we're working with colleagues in Italy. So putting sensors in the water system and measure the parameters of water. And also in the future, so like sensors are going to be very important tools for smart cities of the future. So as to have the control, because without sensors, by sensors, you cannot control different issues like those related to health, environment, and so on. So nowadays, everybody has a smartphone, and it is very easy now, given the capability of the smartphones, to convert these to biosensor. And here just some examples. You see here also, this guy is measuring the lateral flow, same as COVID test. So he's measuring the image and he's transmitting also the results. So everything is going to be fast. So you can see here also a lot of information in this view. But there is a very nice moment for biosensors, given all this explosion of nanotechnology, information technology, and overall the need for these devices to do research in this area, which is really very interesting. And overall, keep in mind that there is a possibility to do this research with not too much equipments and not sophisticated equipments, but with very, very cost-efficient capability. So why nanomaterials? Because nanomaterials, integrating nanomaterials into these devices is offering interesting advantages. So taking advantages of different kinds of nanomaterials in terms of their catalytic properties, interesting optical properties, for example, quantum properties, fluorescence capability, quenching. I will explain you some of the examples. It is possible to integrate these nanomaterials, given also their size, it fits quite well with the size of biomolecules, so usually up to 100 nanometer size, and build different kinds of devices, starting from wearable, implanted devices, standalone devices. So there is a lot of possibility for this kind of technologies. And what we are doing is trying to integrate this kind of nanomaterials. Very simple, you see here, like paper, plastic, and I'll show you some examples. In fact, again, if you want these devices, this technology to be successful, very, very important. So these key factors for their commercialization: cost performance, manufacturing capability, and mass production capability. So otherwise, this technology you may probably develop to create these devices is not going to be successful. We are in this business since many years, so we have been working with quantum dots, with Bohr shell nanoparticles, plasmonic nanoparticles, nanopores, nanotubes, graphene, integrating them even in different microfluidic systems, and even creating some nanomotors. And also very interesting, we have been trying to couple, for example, diagnostic and therapy, the so-called theranostic platforms, or in the area of environmental monitoring, trying to couple the detection of contaminants with the destruction of contaminants. So we call this sensor removal platform based on the network. Let me show you now some examples. I'm not going to enter in details. There is a lot of information. I just want to give you a flavor of the different devices, technologies we have been working with the idea to see also future possibilities for collaboration with different groups. We are looking for collaboration, for synergies, complementary groups that may work together in different European projects or also in a nano context. So I'll start first to show you some examples how we use nanoparticles as new electro-optical labels. Then I'll show you some microfluidics. If you want to do a detection, a biosensor, you need not only to have a very sensitive device, but you need also to handle with the sampling. So you need to find strategies that can probably be useful to pre-concentrate, remove interference. So this is why we use microfluidics double chip technology. Simple is the best, and we work a lot with paper, nitrocellulose. I'll show you why and how we use these materials. Nanomotors, trying to catch even single analyte and bring to the sensing surface for some future application. And finally, about graphene, what we do with this graphene that gave the Nobel Prize to two guys in Manchester 10 years ago, more than 10 years ago, and we are working also together in the European project, graphene inflection. So starting with nanoparticles, this I'm going fast in this, but just to mention, for example, the detection of bacteria. This is an example of the detection of Escherichia coli, you see here. That is detected by using some magnetic beads. So these magnetic beads, in fact, are modified with some antibodies that recognize this bacteria. And then in turn, we use some gold nanoparticles that are also modified with antibodies. So you imagine a kind of sandwich between magnetic beads and the gold nanoparticles and the bacteria in between. So what we do? So taking advantages of nanoparticles, they are well known to induce the catalytic transformation of protons to hydrogen. And this catalytic production of hydrogen is measured by using an electrical system. So by using an assay, we are able to, by measuring this current produced during these catalytic properties, we are able to quantify bacteria and to apply this to quantify bacteria in water and some ground with interest for different areas. And also we moved further in this, we also integrated this detection system. I don't know if you are, some of you are familiar with the PCR system, which is an amplification method also used for COVID detection as a very sensitive way because you can amplify the DNA. And in this way, we are able to introduce inside the PCR cycle the gold nanoparticles and the magnetic beads. So we end up with, in the cycle of PCR, with an amplified DNA and the detect these by using this electrical system. So this is now a patented technology, and a partner in Barcelona is using this for some applications. So the possibilities are enormous. We went further, and in this analytical chemistry paper, we show that we are able to do the PCR on top of the electrode. So we do the same, but everything on top of the electrode. So this is something very, very interesting because it allows you to apply a PCR system that may be also of interest for COVID. In this case, we applied this to detect some plant virus-related nucleic acid. But in principle, you can work for different applications, but just by changing the sequences of DNA. And we measure this by using impedance spectroscopy, which is very, very interesting electrochemical technique that measures the interface between the electrode and the components you want to detect. So moving to microfluidics, as I said, sometimes the life is not that easy as always, but with biosensors, you may have a lot of troubles if you are not able to pre-concentrate, if you are not able to remove the preference. So this is why we have a nice technology. So we use soft lithography process and also thermoplastics. So these are standard technologies used for building microchannels, microchannels. I show you here, you can see it better. So we may produce channels with different shape, size, using different polymers. This is one case using PBMS. And also we are able to integrate inside these channels electrodes. And you see why we do this. So what happens is that if you want to detect in this sample, sometimes you need to run the sample and pre-concentrate on top of the electrodes. And this is why we print electrodes. We have screen printing technology. We use inkjet printing, which are very interesting techniques. You can even print here. You don't print here. You don't need a clean room. And we can print electrodes based on different kinds of materials. And in fact, we are working a lot now in collaboration also with companies to convert even the office printers to printers that can be used for sensor application. Here you can see, for example, just an example of a printer, inkjet printer, that is used to fully print filter effect transistors that incorporate also antibodies. And we are able to print these on plastic, but also on the paper. So this is another case where we printed some reference electrode. In fact, this is a pseudo-reference electrode onto paper. That is also in analytical chemistry, because it was really very simple and very fast to have these. Of course, these are for one use only, just disposable. So working with these microchannels, government chip, and this is an example. I've been working in collaboration with my colleagues in the United States, where you can see, for example, this is the use of capillary electrophoresis, but in a very small dimension. And this comes from a project, Life in Mars. We wanted to see how we can bring these devices for astronauts to use and check, for example, samples directly if there are some amino acids, etc. Of course, they should have some electroactive properties. And we used carbon nanotubes, modified electrodes, and you see here different amino compounds were detected very fast using 3 to 5 centimeter capillary instead of 70 centimeter electrophoresis capillary that we use in a conventional laboratory. So this is also very interesting, and some more complicated things. So we try to combine together sensing of contaminants with destruction, and this is a project we collaborated with Tokyo, with a very well-known group working with boron-doped diamond electrode. You know, the electrodes may be of different material, and boron-doped diamond electrode has a very broad potential window, which is very good because you can do nice detection, but also you can apply high potential to destroy, for example, contaminants. And you see here, for example, as an example, where in the electrodes we are doing some detection of some pesticides, and at the same time destroying them by applying high voltage. So we have a kind of system where we see, you see here, the signals coming from the pesticides, and after destruction, we have almost nothing in the sample. We did the same, but instead of doing application of potential to destroy the contaminants, we use some polymeric compounds. This is a nanostructure based on butterite, calcium carbonate, modified with polyethylenediene, where we did the detection of some compounds, but then at the same time we were absorbing these contaminants and removing this from the place. Or more about this removal of contaminant, we did by using this TMS chip, where you can see this again, but this is very small. It's a graphene oxide modified chip. The electrodes are here. We do the detection of immuno detection, in fact, using some affinities. And afterward, we are able to detect this. In fact, this is a very contaminated, very toxic compound, polychlorinated biphenyl PCBs that are recommended to be detected. So this is also very interesting. Or by using these chips with removal, in situ removal, not only detection but also removal, we were able also to detect heavy metals. So by using again graphene oxide, polydimethylioxane chip, and using some electrodes, we were able to detect some heavy metals by applying electrochemical setting analysis, and at the same time taking advantages of the chemistry of this composite, the bicomposite, which is flexible to remove the contaminants. So these heavy metals. So always working with cost-efficient devices. So cheap is the best, simple is the best. We work with paper, nitrocellulose, and this is really very, very interesting. We are the pioneering group offering a lot of advances in relation to nanotechnology coupled with nitrocellulose. In fact, this is a very interesting material. So working with nitrocellulose is interesting because cellulose is abundant, it is recyclable, biosustainable. The fact that we have these porous matrix, this can induce moving of the liquids by capillarity, so you don't need a pumping system. So you just put the sample and the sample will move, but you should find a way how to move it. Of course, by simple cutting of the paper, You see here different shapes. We can tune also the microfluidics. I'll show you why and how we achieve this. And finally, in the paper, we can integrate nanomaterial and we can convert a piece of paper to a plasmonic paper, a fluorescent paper. So the idea behind this is why not to have sensors by sensors as simple as we have, for example, with the pH paper that in any laboratory we use this, and this is a very old technology, so from decades. So just dipping the paper, you see the change of the color, and you say what pH more or less. Of course, if you need more accurate, you need to use a pH method. But imagine to have something like that for the detection of virus in water, for the detection of heavy metals in water, and the potential is enormous. And these technologies are well known nowadays as dipstick, LFA, microbands, and also here we wrote this review in the Chemical Society review. There is a lot of information about what does it mean working with paper, what are the technologies and capabilities this material can offer. So one of the formats we work with is a lateral flow. Lateral flow is like a COVID test or a pregnancy test, so well known. So this technology, in fact, is well known because it was applied as pregnancy test since 40 years. In fact, I still keep my pregnancy test of my first son. So in Albania it was both, and it was always attracting my attention what we can do more to have this device for other applications. Why, for example, pregnancy test is so famous, it's because of demand. Why for the COVID is also very famous. The problem is that for such kind of application, for example, for the pregnancy test, the levels of the hormone are very high. So it's very easy to detect it. But if you want to use paper for cancer detection, if you want to use paper for very low concentrations of COVID, you cannot do it. You need to do PCR. So how to convert this paper-based technology to very sensitive and to be competitive in comparison to other devices. And here, just for curiosity, for those who do not know how it works, there is a video showing how this paper-based a lot of strategies, and here is, for example, an example where we applied this lateral flow to detect even cadmium. You know, cadmium should be detected, and in our department, the University of Tirana, we have had and still have a very good group working in atomic absorption spectrometry, trying to detect a lot of heavy metals between others. But you need to spend a lot of money, and if you want to offer this as a service, it may cost probably $100 per sample. So in this case, we collaborated with a partner in Florida. They prepared for us an antibody against the cadmium complex with ATPA, and putting everything down in the paper, putting even some extra pads. There were days on this OVA who need to remove some other metals present, usually like calcium, magnesium, and so on. We're able, by using the system, this is in fact a competitive system, it's old, where you can see we have a very nice response. In fact, here is the contrary, so less cadmium you have, higher intensity of line you have, because it is competitive the same. But the nice thing is that we're able to detect up to 0.1 PPP cat, which is fantastic. So very, very nice with this device that may cost less than $1. And we extended this even to detection of uranium. Again, we prepared this in collaboration with Florida. And we sent these devices to our partner then in Florida and applied this to detect the uranium in underground water that were contaminated with uranium. As alternative to radioimmunoassaying that needs professional people and also is more expensive. And they did the detection, by using a smartphone, capturing the image and then measuring these and detecting really very low levels of uranium in water. So more things with paper you can do. You can integrate electrodes, and here we show how we can do electrochemical stripping into the paper. And we put created some channels by using printing with wax. This blue color is wax. So we create a kind of channel. And the nice thing is that when you detect, for example, a dirty sample, that you need to separate the particles and so on. You see here, when you drop the sample, you see here this dot belongs to the filtered parts or the remaining part of the matrix. And then the liquid is going here and is giving the signal here. So we can detect heavy metals by using this simple piece of paper. So this is very interesting for water monitoring. But also, we incorporate inside paper nanomaterials, so we are able to transform a piece of paper to plasmonic, fluorescent paper. In fact, for that we use this so-called nanopaper. It's based on fibers, very nanofibers of cellulose, where we dot with different kinds of particles. We dot with silver, gold, quantum dots, more alpha converting quantum dots. So either by in situ synthesis of nanoparticles or ex situ preparing nanoparticles and dropping this onto the paper. So you can see here how this looks. You have here the paper, which is the most transparent in front of the windows of our institute, and this one with silver and this with gold nanoparticles. So we have now this simple piece of paper with different colors. What we do is we set up, of course, a simple platform to measure with spectrophotometer, and afterward we put this in contact. You see here, for example, with different compounds, with metimazole, iodide, cyanide, urea. What happened is that these compounds specifically corrode nanoparticles because there are some interaction chemistry there. And corroding the nanoparticles, if you corrode, you change the size of nanoparticles, you totally change the optical properties of nanoparticles. So the plasmonics is going to change, and you see here these curves corresponding to the optical response of the sensor are changing, open the different changes of the concentration of this compound. You see here clear changes of the color. So we have this simple piece of paper able to detect these different compounds. Of course, this is not selective. You can imagine that if there are different compounds together, all are going to interact. So trying to do this selective is another strategy we try to apply, playing with antibodies and trying to do it selective for some specific compounds. We also applied this to detect some toxic compounds for visual detection of volatile compounds, for example, by using a silver nanoparticle plasmonic nanopaper, and use this to see, for example, to control the spoilage of food. So we put some gold silver nanoparticles, and you can see here that when the food is spoiled, there are some aminic compounds that are coming, and these interact with the paper. They interact, in fact, with silver nanoparticles, changing totally the plasmonics because they change the size of the particles. So we applied this also to measure in a very simple mode. This is interesting for food packaging, where you can see the quality of the food, if it is okay or not. And this is very, very interesting and still a hot topic in the area of food packaging, but also for smart applications in different areas. Also here, we applied the same nanopaper, coupled now with some fluorescent bacteria. This is in fact a luminescent bacteria. Alivibrio is called fishery. Well known, this bacteria for measuring of toxicity of water. So people working with water toxicity probably have know this bacteria, but usually you put this in a system which is a big spectrophotometer, very well controlled with the temperature and things like that, where you see that in contact with different waters, depending on the toxicity, the first chance of this bacteria is changed. We thought, why not to do the same as we do with this big spectrophotometer, but now putting this bacteria in paper. So we immobilize bacteria in paper, and we are able to measure. You see here different colors coming when you put this in contact with different compounds. For example, we have been working with Duron, TBT, PBD, which are very, very toxic compounds, and we found a nice correlation between the color and the toxicity of water. So again, here one can ask that this is still not selective, but it's okay, and this is probably even better because for some simple application, we need to have a general toxicity rather than the specific toxicity. So I see that I have not too much time. I'll try to go fast in the remaining minute. So you see here, if you want to have more information about the use of paper in this kind of application, we recently wrote this Nature protocol. You can find a lot of information about how to apply these nanomaterials in different kind of designs. So this is what, in fact, the company we have is working with. Let me, move because I want to show you the last part related to nanomotors, where we have been working since years in a NATO framework project with Professor Joseph Wang in the United States, trying to produce these nanomotors. These, in fact, are some nice nanotubes, microtubes produced by electroplating, and we modified this with different compounds, for example, with receptors that can recognize bacteria, for example, in water. What you see here is that these motors contain some catalytic materials, like, for example, platinum, and they are able to transform hydrogen peroxide into water and oxygen. And this oxygen is serving as a propulsive force. And you see here these tiny motors move because the bubbles are coming out, and by having some magnetic properties, we're able to move the orientation of these. You see here better. So what happened with these nanomotors, where they're trying to pick, for example, bacteria in water, or in the Jewish sample, or even in seawater, and even they are able to capture bacteria in different media in presence of different other bacteria. As you see here, this motor is going around, trying to capture bacteria, E. coli, in presence of Cerevisiae. And you see, it's still not capturing, but once this motor is going to see the E. coli is here, is capturing. So the idea is behind this is to capture this analyte and then bring to the sensing surface. So even for single analyte detection. The final thing I wanted to show is with graphene. We are also working with graphene, and this is the last thing I wanted to show, this movie, where you see what the company, our company is doing with graphene. So, a very impressive
technology is on our side to capture what is present around our imagination. It's not what it seems impossible. Why not invest in ingenuity, talent, and technology to achieve intelligent, versatile, cost-efficient, and robust solutions? Why not print our future? This way, we can face all the challenges that appear day after day with new scenarios in such varying environments as transportation, logistics, home, office, or the internet. Graphenica Lab has succeeded in starting from the basis of graphene, the finest, lightest, and strongest known material, the best heat and electricity conductor, almost transparent, flexible and elastic, an abundant element in nature, sustainable, and offering almost unlimited fields of application. Starting from the graphite exfoliation process, we can transfer the properties of graphene to any material, making it intelligent and enabling it to become a sensor for any physical, chemical, or biological task. Even for heating, we do this through a proprietary technology, wax printing membranes, accepting a wide variety of water-based inks at a highly efficient cost, and which can be mixed with biological material, opening a door of infinite possibilities in terms of biosensors manufacturing. This system means a world of unlimited creative possibilities. No matter the shape or the size or the final use, wax printing is possible on almost any type of surface, both flexible and rigid, curved or sharp, performed in-house or in-field, and the results are spectacular. Chemical sensors, physical sensors, biosensors, tactile surfaces or not, supercapacitors, energy harvesters, NFC tags, and more importantly, a practically unlimited range of applications in internet-related fields, including smart transportation, smart home, smart office, smart grid, or smart packaging, as well as wearable devices for diagnostics. Because with Graphinica Lab, we have the technology today that will be indispensable tomorrow.
To end with a very short conclusion. So I wish that with this, I probably convince you that the possibilities offered by nanotechnology, nanomaterials to bring very simple, cost-efficient devices with interest for different applications, being environmental monitoring, one of the most important is enormous. If you want more information, there are several reviews in good journals, chemical reviews about this topic. So just write me if you have not access to these journals. I'd like to thank, of course, all the sponsors and collaborators, so our partners overall in Europe and more. And overall, I'd like to thank all my collaborators from all over the world. We have had also from the region. I'll be very happy to receive. I'm really always excited when people from Balkan are coming, not only from Albania. So for me, Balkan is like Albania. So, and of course, all this area because of my personal reason. So I'll be very happy to see here different languages from the Balkan. So you are welcome to contact me and to collaborate in this area. And finally, to let you know that from 3 to 7 of October, we are bringing again in Tirana the biggest congress of nanotechnology. It's called Strengths in Nanotechnology. With this next time, we put this Nano-Balkan because we want to say that the whole region is going to take care of this conference, organized, supported by Academy of Sciences of Albania, and of course from Spain, with the important list of panels. So you just check the names. They are the most important scientists working in nanotechnology in the world. So you are welcome to join this congress, to present. If you want to give a talk, just write me an email. So excellent speakers will be selected also for keynotes, invited, but also oral presentations, posters. We had Green Time last October in Albania, in Tirana. So this time it's going to be even bigger, even a better place. So it will be a very, very important congress for all the region because we want to support also the creation of this regional center of nanotechnology. So I'll be really very happy to see you all and also other collaborators from your laboratories in Tirana next year. So thank you very much.
Thank you, Professor Merkoçi, for a very impressive lecture. Before opening the floor for discussion, I have one question myself. Most of the time, our homes are empty because we are somewhere else, but we are still heating them or cooling them. Could we use biosensors as a way to regulate, to control heating at a particular time? The problem with using other sensors is that, they don't know exactly who is at home. Because some people prefer higher temperature, others prefer lower temperature. So we know we should, with the sensors and the IT system should actually know for whom it's preparing the room temperature.
This is a very interesting question, but I think there are two things here. If we speak about the sensing point of view, detection of temperature is something very, very well known. It's not a problem. So to have a good, very sensitive sensors for temperature, and there are a range of sensors technology. We are also working with electrical methods where you see the change of the temperature based on measurement of electric current passing through.
My question was more towards the person.
Yeah. I go over this. So the technology is not the problem. The problem is what you said. So how to control and have control of the thing. So I think this is another issue where you need to connect the devices with probably artificial intelligence, communication, IT technologies that would allow you having, for example, different sensors and having also very simple methods to measure and see the preferences also of different people. And of course, you can control that at your house, the temperature, and to be according to your needs. So this is such thing more complex than my expertise, of course, because I work in technology. But I think this is why multidisciplinarity is very important and collaboration. So, and this may be probably the object of a very important project where we need to bring people together to work with us from artificial intelligence and also communication technologies. And this is possible. This is a fantastic idea. So keep this in mind to coordinate a big project for, of course, because you need, first of all, the expert in energy, and then trying to find all the parts. It will be very, very interesting. So
I'm opening floor for discussion, and I have a question here. Shir.
Thank you very much for the presentation. In addition to the energy applications on site environmental monitoring, we saw how biosensors and nanobiosensors are providing different applications for this. But how is the changing in the climate providing technological advances in biosensors and bioluminescent? For example, marine heat waves. They're causing biological and the marine organisms respond differently. So is the demands of climate change pushing new advances in bioluminescents, and what is your evaluation?
The question, so you are asking how the climate change are requesting new development in the area of biosensors. So yeah, of course, climate change is also very, very complex. I'm not expert in this, but the consequences of climate change from one side, but also the reason that caused the climate change. And all, in most part, in addition to physical parameters, are a lot of effects, environment, of course, contamination, and so on. So all these would need and need, in fact, sensors and biosensors to measure different chemical parameters, these different physical parameters. That's why I said also that sensors in the future in the smart cities will be part of our cities. So you need these sensors to be everywhere to control what is happening, for example, with the street drive glare, with the contamination, with the cars and so on, or in water, if there is some source of contamination. So this is also very complex. It is somehow related to the same answer I gave here. So this is very complex. We need a lot of actors to collaborate and to control this. But one of the key parts, of course, are sensors and biosensors. So yeah, this is a very important area of
We have
application.
time for one more question.
Very interesting presentation. In response,
the name of the arm or on surface like a floor heating system. And this ratio of molecular and radiant transfer is a function of age, activity level, gender, many things. So it is very right to extend this question to that biosensors might be legally effective, not only changing or measuring the who's inside, what is the tendencies of conflict, but also so many parameters to allow an energy efficient optimal level of conflict.
Yeah, this is an important question. I couldn't show you more things about biosensors. We also are working with wearable sensors. So, and these are very interesting devices. So you can have these sensors in a wearable format. Even we are working with these. There are also other colleagues working with tattoo form biosensors. So with these devices, in principle, you can measure different parameters. Temperature is probably the easiest way to do it. And then the nice thing is that the sensor you may have wear in your body can communicate with the smartphone through some antenna. And we are working also with these antennas. So through the smartphone, we can transmit and give energy to the wearable. And then through antenna, the wearable is giving back the signal to the smartphone. So I can control, for example, the temperature of my body, and then automatically the smartphone is going to control the temperature of my room. And this is going to do the same, for example, with other members of the family. So this will be the future probably. But I mean, there are a lot of possibilities to couple sensors with different formats and smart sensors, and then of course through mobile phones, artificial intelligence, machine learning. There are a lot of issues that you need to put into place and integrate. But I think these are going to happen in the future, probably near future, some of it. But yeah, a lot of work.